Alright, moving on to lesson 8, abstract syntax trees and errors. After this, I'm going to do the homework, and then after that, I'm going to do the programming assignment number 2. This one's, I'm actually daunted. I'm actually terrified of this one. This one's going to be a tough one. Um, but we'll see. Maybe working with yak or bison will be like a lot easier than I thought. Hopefully I don't have to solve many like LR parsing conflicts and things like that. So we'll see how we go. Anyway, ASTs and errors. Let's get into it. Building abstract syntax trees and handling errors. The payoff of all this parsing theory is that it underpins tools that can generate parser code for us automatically. Some parser generators, Yak, Bison, Cup, are based on LALR. Others, like Antler, are based on LL. Parser generators allow programmers to specify not only a grammar, but also actions to be performed when each production is completed. What should these actions do? Back when memory was expensive, some compilers would directly emit output low-level code as they parsed, often writing it out directly to an external file for later compiler parsers to work on. That implementation strategy saves memory, but has the weakness that the code generated for a given source level expression can only depend on the prefix of the source code seen up to the point where the expression occurs. And this limitation is why languages like C require that all functions be declared before they are used. With such a compiler, implementing recursion and forward declarations requires backpatching generated code with information learned later in the compilation. Generating optimized code is made more difficult, and the compiler tends to end up as a monolithic code that is hard to tease apart into maintainable modules. To support more declarative languages like Java, in which method and class definitions can appear in any order, modern compilers do not emit code directly. Instead, they build an abstract syntax tree during parsing. So that's interesting. What is so it's fast. Sorry, it saves memory. Has the weakness of the code generated for a given source level expression can only depend on the prefix of the source code seen up to that point. What is a source level expression? Let's paste this into ChatGPT and ask what it means. What does it mean by source level expression? A source level expression refers to a part of the source code written in a programming language. It could be a statement, an assignment, an operation, or any syntactical construct in the programming language. The passage, okay. Backpatching is mentioned as a technique to modify generated code based on information learned later in the compilation process. It's a way of updating previously generated code to incorporate details that were not available during the initial code generation. Okay, so a source level expression can just basically be anything in the source code. Alright, abstract syntax trees. An AST is a high-level intermediate representation of the program, in which the constructs of the programming language are nodes in the tree. In fact, a programming language theorist is likely to consider the AST as the true program, with its original parsed representation as an unfortunate necessity for obtaining it. It's important to distinguish between the abstract syntax tree for a program and the parse tree. The parse tree describes how to use the grammar productions to derive the input, but includes nodes that are unnecessary for later stages of the compiler. For example, if using a simple arithmetic grammar, the AST for the expression 1 plus 2 times 3 would not include nodes to represent parentheses or nodes for non-terminals. Right, okay. So that makes total sense. You just want to get rid of the non-terminal, but I mean, by the looks of it, you're basically just getting rid of the non-terminals, which I assume is what we were going to end up doing anyway. But obviously, there's more to that. How an AST is best represented depends on the programming language. In an object-oriented language like Java, it is convenient to design the AST as an object-oriented class hierarchy using method dispatch to execute code specific to different abstract syntax node types. For example, the abstract syntax for a Java-like language might be defined by a class hierarchy with classes like those shown here. So we have a node which can contain an expression, statement, or a class definition. Statement could be like an if or while statement. Expression can be a binary expression or a unary expression. Cool. An alternative approach that sometimes designers use is to have a smaller number of classes to represent nodes, perhaps even just one class. However, this approach is not recommended. It requires that the node class be able to store all the information that any kind of node might have as an attribute, and it prevents the type system from providing useful guidance. If implementing a compiler in a functional language like OCaml, it will be more convenient to express the AST as a variant type, aka algebraic data type, with a declaration like the following. Type expression equals plus of expression times expression, or can equal times of expression times expression, or it can be not of expression, and so on. Okay. It would be more convenient to express the AST as a variant type. Okay. Huh. I never thought of doing it that way. That's pretty cool. Yeah, sweet. Okay, constructing the abstract syntax tree. In a top-down parser, it is natural to have each parsing function return an abstract syntax tree node as its result. Makes sense? For example, the function for parsing arithmetic expressions might look something like the following. Notice that this code will construct exactly the same abstract syntax tree for the expression 3 in parentheses as for just 3. So we parse an expression, we pick the next token. If it's an ID, we return an identifier, some identifier object, and then we have to scan the ID. If it's a left parentheses, we scan in a left parentheses. Expression E equals parse expression. So we scan the left parentheses, then we parse whatever's inside the left parentheses. We do this whole thing again. Then we scan the right parentheses, and we return whatever we parse back to the top level of recursion. That makes sense. In a bottom-up parser, a result can be associated with every symbol on the parser stack. In a bottom-up parser, a result can be associated with every symbol on the parser stack. These results can then be used in the action associated with each production to construct a result when reducing the production. For example, if using the cut parser generator, we might have a rule for addition like the following. Expression equals expression E1 plus expression E2. the result will be a new plus node with E1 and E2 in it, or it can be a number, some number n, and the result will return a new number node for the abstract syntax tree containing the value n, and so on. Left parentheses, expression, right parentheses, we can return a result of whatever the expression is inside it. Cool. Cup allows variable names E2, E1 and E2 to be associated with symbols on the right-hand side of each production. That's very cool. These variables are bound to the results computed for those symbols and can be used as suggested to construct an AST node for the current production. Nice. Cup sounds really cool. For an example, consider parsing the expression 1 plus 2 times 3 with the kind of arithmetic grammar we've been considering. E tends to n, or E within brackets, or E plus E. Consider what happens at the point where the expression 1 plus 2 is about to be reduced using the production E plus E. As shown below. The parser stack, what is that symbol? Sigma? No. What is this symbol? Yes, it's Sigma. I'm promise you guys I'm going to learn my Greek alphabet. I promise one day soon I'm going to do that. I'm going to smash it on Anki. The parser stack sigma contains 4 symbols. The 2 E symbols carry with them the result of 2 previous reductions. The action taken builds a new plus node that refers to the previously created number nodes. Building an AST node during a bottom-up reduction. Okay, so we have before we have we're about to reduce. This E is a number. This E is also a number node. Then we do the reduction, which returns a new plus object with the values E1 and E2, which refer to number nodes. Cool. That makes sense. Error recovery. It is helpful if a compiler can recover from errors in the program and continue to give useful feedback to the programmer. Modern interactive development environments, IDEs, typically report multiple errors. Some can even generate partial code for programs containing errors, allowing developers to test the other parts of the program. How can a compiler recover from a syntax error in the source program? The key idea is wall off syntax errors in the parse tree. At some point in the input, a syntax error is detected. The parser then abandons part of the parse tree, attempting to scan forward heuristically to a synchronization point where there are tokens that follow the bad part. Yeah, so this is panic mode recovery. It then resumes the parse. The following figure depicts this process. The parse tree is shown as a white triangle. The abandoned part of the parse is shown in grey. Cool. That makes sense. LALR parser generators like cup typically support this with a special non-terminal symbol named error that indicates where in the grammar a syntax error can be tolerated. We can think of the error non-terminal as deriving an arbitrary but probably short sequence of tokens. We can think of the error non-terminal as deriving an arbitrary but probably short sequence of tokens. The parser uses this non-terminal when it must to skip past ill-formed syntax. Okay. For example, in cup we might want to catch errors at the granularity of statements for a Java-like source language. We could then add an error production to the corresponding non-terminal. Statement equals error semi, which is of type semi, right? Is that what it's saying? Error. I'm not sure what semi means. So we report the syntax error, return a result, new error statement. Okay. When a syntax error is encountered, the parser uses productions that include this symbol to find a good synchronization point. It first pops the stack until the top of the stack is a state in which error can be shifted. It then scans forward heuristically until... Oh, what does heuristically mean again? I have to look this up. Don't judge me. Heuristically, an adverb derived from the term heuristic. It's a rule of thumb, a practical approach to problem solving rather than experience, common sense. If something's done heuristically, it means it's done in a way that prioritizes practicality. Okay, so we scan forward in such a way that we find a good synchronization point. How this is done is dependent on the parser. Cup scans forward until a certain number of tokens, by default 3, can be parsed successfully without generating another error. Okay. The Yak parser generator uses a less robust technique. If the right-hand side of the production has symbols beta following error, it scans forward until it finds a token in the first of beta. Set of first symbols inside beta. With the example production above, the Yak parser would scan forward to the next semicolon. Oh, right, semi is semicolon. Gotcha. Error followed by semicolon. So we scan result equals new error statement. Gotcha. So this captures any error state and it gets cancelled, well, it gets finished on a semicolon. That makes sense. Okay. Where was I? The Yak parser generator. With the example above, the Yak parser would scan forward to the next semicolon. More sophisticated techniques try to find the optimal synchronization point. In recursive descent parsers, error recovery can be implemented manually along similar lines. Errors can cause exceptions, and exception handlers can implement error recovery. For example, we might implement a statement level error recovery as follows. So we parse, we check the next token, handle different statement types. If it's one of these, if we catch an error, then looks like we keep scanning up until we hit a semicolon. Then we scan the semicolon. I'm guessing we're just discarding tokens here with an empty scan function like that. So we discard up until the next semicolon, and then we return the error statement. Cool. Doing more sophisticated synchronization is difficult in recursive descent parsers because the parser state is not exposed as an explicit machine. As examples have shown, error recovery does not mean that the compiler has to abandon abstract syntax tree construction. Instead, it can generate special error nodes in the AST that are treated specially by later compiler stages. For example, it would make sense to skip error nodes when type checking and when generating code, to omit code that halts the program with an error message. This strategy enables early testing even before the code fully compiles. Okay, that's cool. I don't understand what this means. The parser state is not exposed as an explicit machine. I need to plug that into ChatGPT to get some more info on that. Let's see how it deciphers that. Here we go. The parser state represents the current position or parser state not exposed explicitly. The parser state represents the current position or progress of the parser in the input stream. In recursive descent parsers, the parser state is not explicitly exposed as a machine or an object with easily accessible internal details. Right. Okay. So the current parser state is not easily, it's not easily analyzed, I suppose. The parser state is not exposed as an explicit machine. Makes sense. Okay, that was a super quick lesson. I there's not much in here that is confusing. This is pretty well straightforward. Do we have any readings? We have the Appel book. I don't have that book. Video example slides. What do the slides say? Let's see if we can get this going again. Is this going to open? Probably not. Where are we? AST slides. Let's try this again. Building the AST. Java statement attached to each production. Returns a result, which is a node in the AST. Plug that into the AST. How not to design an AST. Introduce a tree node for every node in the parse tree. Obviously, you don't want to do that. You just basically want your non-terminals. So it's a simple-minded approach to only have one class. That makes sense because you want different types for each node, right? You can't just have a single type for everything. Need information for if, while, etc. Must have fields for every different kind of node with attributes, not extensible. Yep, that makes sense. Can use subclassing to solve the problem. Yep, so you derive classes. Write abstract classes for each interesting non-terminal in the grammar. Write non-abstract classes for almost every production. Add extends expression, multiply extends expression. I wonder if we will actually need to turn in the assignment, whether we actually need to turn a parsing tree into a abstract syntax tree. Or whether Yak essentially does that. I guess we'll find out. So next lesson, going to be the homework. Then move on to the programming assignment. This is it's supposed to be a group assignment, so it's probably going to take me maybe a couple weeks to do. I'm not sure. Just doing it in my spare time after work. So yeah, there may not be another video for a while. So thanks for watching. I'll see you in the next video.